Why do we need to know about measures of central tendency? Well, we need to be able to understand the locations of large amounts of data, which can be summarized using simple measures to best represent that data as a whole. And why is that? Because these kinds of summary values occur again and again in 99% of the data that we deal with. Now, before we start off with the session, I'd like to inform you guys that we have launched a completely free platform called as Great Learning Academy, where you have access to free courses such as AI, cloud, and digital marketing. You can check out the details in the description below. Now, let's have a quick glance at the agenda. We'll start off with a bit of exploratory data analysis. Then we will understand what is statistics and look at the different types of statistics. After that, we'll dive into measures of central tendency. And finally, we will look at the measures of deviation.
So stats, the outline is basically these are the different things that we are looking at. Like here are the topics. We'll look at why statistics, what is big data, relevance of statistics versus big data, definition of statistics, different types of variables. We'll touch upon the terms like population, sample, parameter, statistic. We'll come to all of that. Then types of data, we briefly touched upon there. We'll delve deeper a little bit. Then we talked about data objects, attributes, everything. Then central tendency, one of the most important concepts in statistics are very basic concept of the statistics. And 3Ms. 3Ms are the measures of central tendency. Actually, there are 5 that are there, but 3 is the ones that predominantly we use. We'll touch upon that. Then what is dispersion all about? Then we get into descriptive statistics, coefficient of variation, and basically summary of all the videos that you have seen, we can run through. Right. So why statistics is important? There are 3 different events that have been mentioned as which are driving the importance of statistics of late. Statistics has always been important, but in the current scenario, statistics is gaining even more importance because of 3 reasons. What are the 3? One, of course, is mentioned in this one in the event 1. You can see technological developments, internet evolution, things. But what are the other 2?
Understand the real problem and act on it.
Right. So see, it's all about the technological evolutions, internet of things coming into play, large amount of data getting generated, because of which there is a lot of patterns that you can identify compared to past. When data is less, you see less patterns. When data becomes humongous, you see large patterns emerging. There are some factors that are influencing. I think the question about how do I draw the connections between the things? Definitely the data related stuff and the evolution of internet is one thing that is caused. But we touched upon something that has to handle all this data also. So there is a backend architecture,
Big data.
hardware essentially. Where is the data to be stored? Unless you have a ability to store that amount of data and process that amount of data, you need for that which you need a computing power. Collecting the data is useless. Data has always been in place, but there is no way to store that data. Now that capability to store that data and process the data with the advanced computing power is leading to these changes and emergence of importance for AI and ML space. That's the second one. And what is the third one? The cloud computing and everything that is coming into play. So the event 2 is enormous computing power, as I talked about, and analyze massive amounts of data. Then faster algorithms, solving problems, visualization that we talked about right now all this while. Then storage capability, parallel and cloud computing. These are the 3 primary events that have led to this explosion of data science in a broad scenario. Then what is big data? I know I already shown the things, but what is big data? For me, this is the best and simplest of the definitions. Any data that you can manage with the traditional form of software, traditional form of storage, traditional abilities, can be considered as a normal data. Something that cannot be managed by the traditional, and you need advanced or more distributed architecture to solve the things. That's where the big data comes in. The standard definition of big data calls about these 5 things. One is volume. We know there is a huge amount of data that is coming into. That's why it's called big data, but that's not the alone thing. And you need an ability or the computing power to process that data and come up with insights at fast pace. That's what velocity is about. Variety is you need to be able to handle different types of data. not just one form of data that is out there. So I have some come up with some algorithm, solve NumPy, all numerical data, fine. But what about text data? What about speech? What about audio? Different types of data that are out there. So you need to be able to handle all those types of data also. Then at the end of the day, you should be able to gain value out of that particular one. And lastly, veracity. What does veracity mean? Veracity is about the truth or the accuracy that the data provides, how much you can rely on the data, the reliability and the accuracy that the data holds you. Well, there is a lot of data inside it, but I cannot make total sense of it. I may be 50% true that is happening, but I'm not sure if that completely is the same. Than that, the data should be able to tell you that veracity part. So it means accurate, it is consistent, accurate, and you're able to rely on that data, what it is throwing at you. That's what veracity will be. Of these, all these 5 parameters will decide whether that big data is meaningful and you can bank on it and you can leverage it for your applications. Now, different statistics methods. So you have a lot of customers, segmenting those customers into different groups, understanding patterns, or which kind of customers exhibit what kind of a behavior. We are calling, for example, brand switchers, long-term customers. We talked about loyalty also. If my customer is loyal, I can extend some promotions to him. Or if some customer is just in a tentative phase, how can I make some promotion offers to that guy and retain him? What is the kind of strategy that I should go with, a loyal long-term customer versus a person who is switching between the things? My strategies cannot be, so how should I adapt myself? For that I need to understand these different types of customers. One example we talked about. The other example could be temperatures, or water scarcity available in different things. What should the government take, for example, different strategies to conserve water or to provide water continuously so that people do not face challenges? Can I come up with my strategies based on geographic locations? We saw water problems in Tamil Nadu, we see water problems in Karnataka, we see water problems in elsewhere, something like Nagpur and other places also. But the kind of problems, what causes it, and the solutions are very different. Can I come up with the reasons and underlying patterns as to why that happens? That's what some of the classification methods can explain you. Pattern recognition. So the visualization comes into play. I think I used this quote last time: a picture is worth 1,000 words. So
Ram,
histogram box. Yes, sir.
yeah, just one question. Sorry to pull you back into the big data thing.
No
Uh,
problem.
Anything that like all these statistical methods and the tools that we are doing or we are learning right now, maybe we started learning, are they
Yes.
also implemented as part of big data? Because why I'm asking is, big data, is it continuous, or is there a is there a, I wouldn't say limit, but because all this data that we are analyzing, they are loaded on to a system, right? But is big data
Yes.
continuous?
I think this course is the answer to your question,
Okay.
because why do you need to do machine learning in the first place? Why? Let's say, for example, you have a finite set of data and you're not capturing more data. You know everything about data. Over a period of time, you can capture everything and there is nothing to be known. There is no question of machine learning. Why we are doing machine learning? Now, in my data, I have seen this behavior being exhibited. When new customers come in or when new data comes in, something new that I have not seen happens. Based on my analysis of this data and the model that I built on this one, can I apply this to new data? And as much as the new data coming in, your boundaries are expanding, your horizons are expanding, essentially. So big data is all about that. That's what we talked about, the volume in the big data phase, right?
Okay.
As you get new data, you have to apply the model that you built on that new data. Then there is a real test for your model, whether your model will stand the test of that new elements that are coming in, which is not seen, and it can be robust to see all the variations coming in, or it cannot hold it and then it just fails. Then your model is not robust enough. You have to go back because you have not considered some of the parameters. You need to take them into account, rebuild your model and do all other exercise. So machine learning, the courses that you're doing are very much applicable in the big data space. The only thing is, you may not handle that much of the data that you handle in real time for this course, because this is more about the learning phase. But when you get into the real world, it is very chaotic. You can't even think how much time you need to spend in terms of understanding the data and cleaning the data than building the model. So this is what we keep hearing in the data science parlance. A data
Okay.
scientist spends 20 to 30% of the time in identifying what data to be procured, 30 to 50% of the time in cleaning the data so that the data is ready for building a model, then 10% of the time in actually building the model, and 10% of the time in interpreting the data, because the data that you get is very, very garbage, total garbage. You have to really clean the data to make the data model ready and then apply model on it. Otherwise, you put garbage into it, you get garbage out. It's called GIGO, garbage in, garbage out. That's where it stands, right? So we
Right.
talked about pattern recognition. I'm assuming there are no more questions on pattern recognition. If anyone has, please raise. Otherwise, we can move. Okay. So association. So now association is an important thing. So the example that Abhinandan used in the classroom for you, so that I'm using the examples in the video is like somebody is buying coffee. Those guys are likely to buy bread also along with that particular one, or buying milk is likely to buy sugar along with that one. So the standard examples that go tells you the association. So I go for buying something, parallelly I do some other activity. Is there an association between those two? Something like we talked about earlier, is the temperature increase is connected with water scarcity in a particular city? Is there an association? There is an association, but is there a cause and effect relationship? We don't know. So there are two different elements here. One is an association, second one is causation. So causation comes into play when you start building a model, you start predicting something, because this causes this. I know that this is a function of this particular one. Then I can build a causation, build an equation and work on that one. Otherwise, I know there is an association. But what I will not have a sense is how they are associated. What is driving that? A is increasing, B is increasing, fine. But is A is increasing, B is increasing because they are connected? May not be. There could be a third factor, C, which is influencing A as well as B. Because C is varying, A and B are both are increasing. That doesn't mean A and B are connected. So that's called spurious correlation. We'll touch upon when we talk about correlation. But there is an association between the variables. So do we bother about the association genuinely versus we should not take into account association because they are not directly connected? I hear the standard example when we hear in any of these classes. One is temperature in India is increasing, and probably sales of particular product in US are increasing. You just take those two numbers and they're really going up. Does that mean this is connected? By no means. Just because there are two numbers, that doesn't mean that they are connected. Are we in sync on this one? What association is all about? Association basically helps you understanding relationship between these two variables, but what I'm talking about is a caveat, not just because statistically you do a calculation, it shows a value of high correlation like 0.95 point something, doesn't mean that they are really connected. That's where your business understanding comes into play. You really need to see what is causing that connection. Just because two variables are increasing doesn't mean there is a definite analysis. So some of the analysis that are out there, association analysis and some of the things, help you break into that particular one and see how those relationships are between those variables. Most of the times you do this analysis on association levels only when you are clear that those variables have some kind of a connection between them, and that is determined by your business intelligence. So the last point is mentioned here. This can be adapted by organizations to stay low, item bundling, because as I said, coffee versus milk, milk and sugar, or coffee and bread, some of these things. So the item bundling and all these things can be done because people find that there is an association in purchase behavior. Predictive modeling, we touched upon this right now. So rainfall, temperature increase, water scarcity, they are connected. So water scarcity is a function of rainfall available and the temperatures that are there. So how much temperature increase has a role to play, and how much rainfall has a role to play. If it is 50%, 50%, 30%, 70%, or 10%, 90%, that you can build a model to identify the impact of each of these variables on water scarcity. So that's about predictive modeling. So you'll predict water scarcity based on those two variables. It's one of the simple examples. So there are different ways to look at that particular one, different examples that come in as we go through the course. For the interest of or for the just my feeling of creating more confusion, I'm not getting into this regression, logistic regression, which has been touched upon the course in the videos, but I'm holding on myself from going there. Predictive modeling is the regression we talked about. One is a function of other two variables is regression. We can talk about that later in subsequent classes. That's one example that we talked about. So we touched upon regression. The other pieces will hold on, right? The next one, uh, classical definition of statistics. So basically statistics is all about specifically adopted to the elucidation of the quantitative data affected by market extent and multiplicity of causes. So basically there are different factors that are influencing, because of which you get a lot of quantitative data and you come up with methods to make sense out of that particular data. That's what statistics is all about. Thomas Davenport says business analytics and notes the similarities and dissimilarities between the two. So I think he quoted Thomas Davenport in the video, which talks about business analytics is all about defining a broad use of the data on quantitative analysis for decision making within organizations. That's where statistics comes into play. That's where business analytics and statistics are like hand in hand. They're hand in glove kind of a thing. You use a lot of statistics for doing business analytics. Now, this one we touched upon last week also, descriptive statistics and inferential statistics. So descriptive statistics is basically talked about summarizing the data. It is what is happening with the data, maybe through visualization, maybe through a couple of statistics, something like mean, median, mode, or some of the things that we have seen. And you summarize the data, get a sense of the data. That's what descriptive statistics is all about. And that will help you to form a hypothesis. And once you have a hypothesis, inferential statistics comes into play. You basically use inferential statistics to validate the hypothesis that you have formed. But why should we form a hypothesis? Now we are jumping into one important question. Why should a hypothesis be created in the first place?
To solve a problem or to solve a question?
Right. So
prediction, right? It's a prediction.
Prediction to an extent, yes. Solving a problem, yes. But there is one important facet why we have a hypothesis to be defined, and inferential statistics coming into play. So hypothesis at the end of the day is which is not proven till now. It is an observation that you have come up with, the data or the summary that you have seen. Do we agree on that one?
Yes.
So now it is your intuition telling me that this is something that is a possibility, because of which something is happening. You have your sales going down, as an example, the business came to you. Now your intuition is that there is a new competitor that has come into play, which is eating into your market share. That is your intuition. Because of your intuition that say that new entrant into the market has led to decrease in sales or decrease in revenue, whichever you call it. That is your hypothesis. You form the hypothesis. So based on that one, now you go deep down, start dwelling deeper and validate that particular one. But when you are doing validating, what are we trying to do? You took a sample of data, some observations, and based on that small sample of the data that you gathered, you realize that this is what I am observing. So for example, in the previous honey production example that we have seen, there is a drop in North Dakota, for example, in that particular state. Production between honeybees, the number of colonies and yield per production is going down. I'm randomly making up variables, not exactly remember what is there, but giving. So the yield per this thing is going down, and honey production is also going down overall. So now my hypothesis is, I don't know about North Dakota alone. Now I say that because of this connection overall data, I'm seeing that there is a drop. I'm saying that the honey production is coming down because the number of colonies are going down. Now I make that as a hypothesis, and based on that, I go and extrapolate that hypothesis. Is it valid across all the states or in some states versus what is happening? That's my hypothesis needs to be proved. So essentially what I am doing, I am taking data at a small sample level and extrapolating that to the whole population. So the way of validating your information to be true universally is the objective of inferential statistics. Are you understanding something? We'll take a small example. There are some bulbs that are being produced. So the hypothesis that I have is 10% of the bulbs that get manufactured would be defective. That's what we'll tell, we accept. So business will plan for it as a contingency plan, and if we get 10% of the bulbs at any point of time, we account for replacing those bulbs or losses, whatever, we'll account for that. But how did I decide that 10% of the bulbs are faulty on an average? We produce 10 lots of bulbs, each lot, let's say 1000 bulbs. We produce 10 lots, which is 10,000 bulbs, and across 10,000 bulbs, we saw 1000 bulbs to be faulty. So we agree with that particular one, bank on that. But in the next 5 years, if I'm going to produce another 5,000 lots or 10,000 lots, is it that it should be remaining as 10% only? Or by some reason it becomes 25%, which is beyond my this thing. All my calculations, my business planning, everything goes for a toss. So can I really be sure that it's only 10%? Or maybe 12%, 11%, and not 25%? How can I be sure? So I'm extending the information that I gathered, the hypothesis that I formed based on the 10 lots that I used for my hypothesis, and validate that on the broader population. The process that you do for confirming that to be a true or false versus you can rely on that one or not is the scope of inferential statistics. Because this is something which is important as you go through your modeling, as you go through your this thing, the concept of sample versus population needs to be understood clearly. Majority of the times you don't know what your population is, and almost always all you have is sample at your disposal, and through your sample you will make an inference and you statistically try and validate that hypothesis that you found based on your sample, and then you apply that to your population.
Even in today's context, if you say that with so much of data available, we can measure every data, but still, if you think of the futuristic data, that still the today's data becomes a sample, right? So from
Sample, exactly, totally. So because I can, my population, as someone asked earlier, is my data is continuously increasing. So how should I look at it? That's how it is. How much ever data you have at your disposal, I'll consider that data as sample only, because tomorrow more and more data is getting created. So that all becomes my population. I don't even have a view of what my population could be. So you have to operate that sense of, I have a hypothesis and I need to validate this to be sure that this can be applicable and this is valid even when my data increases. My data increases, or I get a hold on something that I have not seen today. That's the scope of inferential statistics.
constructing a right hypothesis is still crucial, and which needs
Very crucial,
right?
and it's a very crucial point, very important point, and hold on to that thought till we go to hypothesis testing in the coming weeks. And if you don't have a valid hypothesis or the correct hypothesis, your whole business question goes for a toss. This is what I said. Take the simple example we talked in the beginning of the class. You go to a doctor, you get temperature, doctor gives you paracetamol, temperature goes down, and he assumes, let's say, that this is caused because of viral, and he give you one antibiotic, and your temperature is not caused because of that antibiotic, that viral only. Something else is causing, some other infection in your body, something is causing, and you used antibiotic that is not at all related to. How do you think about it? It's a totally business wrong hypothesis formed. We see these instances time and again happening in business also, right? Because most of the times we try and treat the symptoms and not the causes. The problem goes in a completely different direction. Fair point. So let's go further on this particular one. So as I said, now you understand the difference between population and sample. Sample is all the data that you have at your disposal to do analysis. That's the sample. Population is much bigger, and which is not known. Most of the times population is not known, or even if you know, it could be ever expanding. So imagine that population is a construct that is much holistic in nature, much comprehensive in nature, which we cannot handle given the resources and abilities that we have. But our objective is essentially to make any inference, any insight, any prediction at a population level and not at a small level. That's what the whole purpose of ML, AI, whatever we do is at a population level. Okay. Then sample. Sample is the selection of observations which is at your disposal, and sample is a subset of population. That much we should be sure about. And from a population, you can pick n number of samples. So you have 100 students in a school, or 1000 students in a school. I can randomly pick any 100 people and talk about how is your school. Is your school good? Are you getting good lessons? Are they offering you good sports facilities? Are they giving you good recreation facilities? We can ask a number of questions, picking up any random sample from that population. So the sample should be representative of your population for your information to be, or your analysis to be accurate. So that's one step ahead. But the connection between sample and population is sample is a subset of population. Population is more comprehensive and definitive in nature. And most of the times you don't know population. That's the two key important points about sample and population. Now, what is parameter and what is statistic? So statistic is nothing but a singular term of the statistics that we commonly use. So a statistic is any metric that you calculate on your sample. Basically, for my sample, as I said, I have 10 lots. Each lot is 1000 size capacity. 10 lots of bulbs I produced, so 10,000 bulbs are there. So that is my sample. So how many are faulty? The fault number of faulty bulbs in my this thing is a statistic. So on an average, if I calculate, the mean value that I calculate is a statistic, or the standard deviation could be a statistic. We'll come to standard deviation, what it means. Any metric or a measure associated with a sample is called a statistic. There are some standard statistics that we measure. So this thing is related to sample. But if you calculate the same metric, what you're doing on a sample, if you calculate them at a population level, it is called as a parameter. So parameters are calculated at a population level. Statistic is calculated at a sample level. Those are the terms to keep in mind. Now, coming to the data sources, primary data, secondary data. Primary data is most of the times captured through a live interaction, a survey that happens, or at the with a specific focus, specific objective in mind. You capture that data. That's called as primary data. And most of the times it is associated with a specific objective, but over a period of time your primary data becomes secondary data because it becomes part of a panel, it becomes part of an archive, it becomes something somebody else gathers that data which has been done in the past and use that for further analysis. So that's why that data at the end of the day becomes secondary data after a point. But this is primarily collected with a specific objective in mind. Here there is no specific objective, but you collect data historically over a period of time and archiving that information. That's what secondary data is primarily all about. Types of data. Now we touched upon qualitative data, quantitative data in the past, and continuous and discrete, two different types. So qualitative data, we saw, which is your categorical variables and nominal variables, is your qualitative data. Even your ordinal data is qualitative data. Quantitative data is again broken into discrete and continuous, as we have seen in one of the previous slides. So that's why I'm not spending many time, more time on this. Is anyone any more questions on this one? Okay. So now types of data sets. Now it is important to look at, so we know primary data, secondary data, continuous and different. So we need to have an understanding of which data is of what nature essentially, right? For example, I have an audio clip, songs. Do we construe that as data?
Yeah, it is data, right?
It is data, right? So let's say, for example, a newspaper's collection of newspaper articles. Is it data?
Yes.
It
Yes.
is. Yeah.
Stock market trends for a specific set of mutual funds. Is it data?
Yes.
Yes.
So can I store stock market data in an Excel sheet?
Yes.
Stock market, yes.
Yes. Can I store a music file in an Excel sheet?
No.
No.
Then how do I handle the data?
It's a format is different, right? You have, it's a music MP3, MP4, whatever.
Right. But now let's say, for example, I want to understand all songs or all music composed by Beethoven. I'm just taking an example. Beethoven composed a number of symphonies. I want to come up with some common patterns. As soon as I see this kind of a pattern, it's a Beethoven music, not Mozart or not somebody else, Vivaldi or somebody else. It's Beethoven. How do I do that? To do the data on an MP3 format or wave format, whatever it is, how can I do that analysis coming up with a machine learning algorithm or a data science algorithm on it?
I mean, you need to have some parameters associated with that data, right?
Right. So that at the end of the day, even an MP3 is a file, right, that is stored on your disk, on your system, or somewhere. So the data is at the end of the day digitized into zeros and ones. So it's a sequential data that is out there. You're getting what I'm saying? It's a sequence of characters, sequence of information that is laid out in a specific format that you can start using for analysis purpose. So you have to break the data in a way that is more meaning for you to handle and at the same time analyze. So any data can be constructed and changed into a format that you can do analysis. So compared to historically what the data has been mostly quantitative that is there in place, now you are seeing all different types of data. So here it is referring a graph data or network data. So how can a graph data can be stored or a network? So you imagine network, right? The moment you see network, there are multiple dots out there. Each dot is connected with all other dots through certain lines and these things and everything. That's what network is all about. So if I have to store that network information into my system, how can I use?
It's probably image.
Image might not serve fully, because at the end of the day, the moment you make it image, it becomes a two-dimensional image. Then you run into missing of some information. But sorry?
Mapping of nodes.
Mapping of nodes. So how does that work? So I'm just trying to make connection to one of the points that we did discuss earlier. I was actually hoping or assuming that somebody can connect the dot. See, we talked about linear algebra in the beginning.
In the matrices, yeah.
Matrices. So network is nothing but a matrix. So let's say, for example, you have 100 nodes in your network. So you put 100 columns and 100 rows, like same rows and columns, same set of values as you have seen in a pair plot or somewhere. And if there is a connection between one node and other node, you put 1. If there is no connection, you put 0. So that's how you identify connections between different nodes in a network. Is that fairly represents than an image? This is a better representation, which can be manageable.
Yes.
But in the end, what are we creating? A matrix. And as the number of nodes in your network are going to thousands, let's say Facebook network, how many people connect with each other? How do you draw the networking there? Phenomenal. So how many zeros and ones? There would be less ones and more zeros at the end of the day. So how can I store that data? How can I process that data? So that's where matrix algebra comes into play. Linear algebra comes into play. I'm just giving an example of where maths can connect the dots into the scheme of things at the back end for you. See, this is more about getting an intuitive idea of the different data types that are there and what kind of problems machine learning algorithms solve. See, for solving most of the normal standard data that we have, numbers and everything, machine learnings and these things are required, but other pieces also can do. But solving some of these advanced problems that are there, like computer vision, image scanning, image analysis, or detection of patterns in videos, all those things essentially require advanced algorithms, and you need advanced ways of storing that data and processing that data. That's where ML comes into play in processing all of that. Right? I'll just move on in this one. So the data objects, I think last time we took an example of, in the last class, I took an example of a fan. If you take a fan, fan has an entity, fan is an object. But within fan, you can find a motor, blades, power supply, and capacitor. You can do different things. But what a fan does at the end of the day, switch on, rotate, speed variation, switch off. Four functions that it does, behaviors, and it has different properties. Similar to any object you take, for example, a customer, you contain a lot of data about the customer. You contain customers, let's say in a medical base, let's say it's easy to connect. For a patient, how many times he visited a doctor, what are prescriptions has been given to him, what medicines has been consuming, how long he has been a patient with a specific doctor, how many times is coming up, all information can be captured. That's all which is can be tabulated. But there is an information, something like the scans, images, or diagnostics documents of that patient's records can also be stored in connection with that patient. That's a medical database essentially. So all information connected to one particular patient is an object. Here the patient is the object, and all information related to that patient can be the data or entity properties of that particular patient. That's how a data object will come into play. I think I touched upon the OOPS concepts last time, but this is another example of the same thing. Now attributes. Somebody talked about the binary here. So nominal we touched upon. What is binary? Any data that has only two states.
Two states, yeah.
A 0 or a 1, a yes or no. It's basically Boolean in nature. So any data that can be represented in those two forms is called as binary. So there is another level of detail provided in the video, which is called as a symmetric binary and asymmetric binary. So basically symmetry is all about the convention that we follow. Asymmetry is a non-conventional format. So for example, you are doing a case study on identifying how many people have a heart disease. So normally 0 indicates for us there is no heart disease, 1 indicates that there is a heart disease. We flag all the people having a heart disease as 1 and all the people who do not have a heart disease as 0. That's conventional. But it doesn't matter actually whether you flag 1 0 or 0 1. But if you flag the things or label the things in a non-conventional way, it's asymmetry. Just that much. There is not much of a difference between symmetry and asymmetry that we talked about. Okay. So now ordinal. Ordinal, I think we talked about the ordinal side of the data. It is good, bad, ugly, or high, medium, low, those kind of ratings, anything that comes in, you know that you can put across an order, but there is no way to calculate how much is the difference between a good versus bad, good versus ugly, or any of those things. That's the ordinal data. We look at examples where we look at the ordinal data when we look at the things. So that's primarily the fundamentals of statistics and everything. So we'll quickly run into the measures of central tendency because we have seen the plots, histograms, and everything. Let's quickly that. So raw data. So let's say, for example, I capture marks of 100 students in a classroom for a particular subject, mathematics. So if I have all 100 marks of 100 students, 100 numbers, so what is that called? It's a raw data. But if I categorize that into what is the average marks that a school has got, and what is the distribution of that marks in a classroom, how many people have got less than 50, how many people have got more than 90, and if I start putting that information and classifying that in a way, I am moving from data to information because I'm processing it. I'm trying to gain more value, more insight into the data, what it is. That's what the information is all about. And to do that transformation of raw data to information, the basic technique that we use is frequency distribution. So frequency distribution focuses on classifying raw data into information. It is used as a data reduction technique simply. So this is it is. Let's say how many people have got 0 to 10 marks, 10 to 20 marks, 20 to 30 marks, 30 to 40. Like that, if I go and create and I create 10 classes and distribute all the marks for the 100 students across these buckets, then that tells a histogram for me. And how do I, the important question is, how can I decide how many classes, what it is? So there is a business logic to it. One, you can see what business makes sense, or there is a statistical formula that is out there to define the number of bins. We can come to that when we start actually doing frequency distributions. But generally, most of the times, if you create a histogram chart in your data, it logically, intuitively takes that formula into account and it creates the number of bins based on the data distribution. That's about histogram. What is central tendency?
Which talks about how the data is, centered around, or the central values of a data.
Yes. So as you gather more and more data, means your data points keep on increasing. So there is a natural tendency around a value. All your data points will be clustered around a certain value. That value is called as a central tendency. So basically, imagine a human behavior. As soon as we go for a conference, thousands of people come into a place. So if certain people start sitting in one corner of the place, majority will start sitting there only. You hardly or unlikely you see that one person going and sitting in another extreme corner, which is no way. Like one person is sitting and 100 people are sitting. It doesn't happen. So you generally conform to the norms. You generally conform to the things. It's not because they want to conform or anything, but that's the nature. That's the behavior. Most of the data tends to stay around a central value. That central value is called as the average of that data. And central tendency talks about that behavior of the data points to cluster around that average. That's what central tendency is all about. Is the concept of central tendency clear? Because this is a very basic tenet of statistics. All right. So now, as I called it as average, there are different measures how you can measure what is that central value of the data. where all the data points are clustering around. That's what is called as an average. There are 5 averages essentially that can be calculated. There is a mean, there is a median, then there is a mode. That's these 3 are predominantly mostly used in broader applications, general applications. That's why we always talk about only those 3. And they are called as 3Ms. But there are other 2 which are not covered here, but I'm just giving as a information for you. One is a geometric mean, the other one is a harmonic mean. They come into application in specific scenarios. They are not a regular application, regular scenarios, but very specifically, very rarely they will come into usage. I'll cover those 2 at a later point for now. But harmonic mean, you generally have a sense of where you calculate. Let's say you calculate time taken for a person to travel between 2 towns, essentially. Point A to point B, it took 3 hours. Point B to point C, again point B to point A back, it took another time. How much time it took, you calculate a straight average. But he goes with this much speed while going and this much speed while coming back. You cannot do a plain average of 2 speeds, because while going it is a 40 kilometers per hour, while coming back it is 60 kilometers per hour. It cannot be 50 kilometers per hour average, because that's a plain average you are calculating. That doesn't work in that scenario. You have to apply harmonic mean. But that is just for information's sake. If needed more information, I can provide that. We'll just move on there. We'll touch upon each of these things. So what is mean?
Just the average.
Just the plain average. And the properties of mean is every data point in your data set will be taken into account for calculating mean. First thing. So mean is a true representative of every data value that is out there. Having said that, which is a very good characteristic to have, then it also comes with a caveat or a disadvantage. Let's say, for example, in a class, all people of 100 people, most of the people got 30 to 40 marks, around 70 people or 80 people, and remaining 20 people got above 80. And if I calculate the average of the class, the average stands somewhere around 60, 65. So is the average fair representative of how the class is performing? No, because people who got 80 and above are actually skewing the performance of the other candidates. Maybe there is a genuine reason the concepts explained in the class are not understood. But certain people, maybe for whatever reasons, have ability to respond on the exam. The respondent got good marks, but that is not a representative of the classroom. So mean has that kind of a disadvantage, but still it takes into account all the points in the classroom. But it is tend to vary based on extremities or the outliers that are there. That's the point to be kept in mind. Then median. The good part of the median is it doesn't take into account the outlier influence of the outliers into calculation, because it is primarily focused on the positioning of the data. You sort your data in a particular order and you find what is the middle value that is there in the data. That is referred as a median. So if you have even data points, the center 2 values you take, let's say for example 10 values, you have 10 values in a data set. So you calculate the 5th and 6th, and then you calculate the average of those positions and come with a median, the positional average essentially. So if you take 11 values, 6th value becomes the median. So but the important constraint of this data set to be, you have to arrange your data into an ascending order or descending order. It doesn't matter whether ascending or descending, because it is more about the central position in the data. You need to capture that, and then you can calculate the median. The advantage is it does not get influenced by the outliers, but the disadvantage of this particular one is
when the count is even.
No, count is even, we come up with a formula. Let's say for example n is even, so it's, let's say 12 plus 1, 13. So you calculate a particular term in that particular one, in that particular series, and let's say for example 12 terms. You take 6th and 7th and calculate the average of the 6th position value, 7th position value, and you calculate the median. So that is also can be done.
Okay.
There is something that mean can do, median cannot do. Let's say for example in your class you have 3 groups: section A, section B, section C. You get mean for class A, section A, mean for section B, mean for section C, and you can calculate the mean for the whole class by calculating the average of those 3 means. But if you get a median for class A, median for class B, median for class C, can that be the median of class ABC together or section
No.
ABC together?
No, you can't do that. Yeah, right.
That's a fundamental disadvantage that median brings in. So that's why another metric got into play. That's about mean and median. So then there is third metric that we call as mode. Mode is also not influenced by the variations in the data or extremities in the data. What is mode primarily bothered about?
I think the highest frequency, right?
Highest frequency, yes. And now let's say in a class of 100 people, 98 people got between 1 and 50 marks. 2 people got 55 or 95, whichever the number is different. So would 95 become the representative of that class?
No.
No.
You understood the question what I'm asking, right?
Yeah, yeah. It's
So
not the outlier, it's the average, I think the central one.
But we are taking mean, median, mode as the representatives of central tendency, because mode is also a form of central tendency. Just because by frequency count it is just one more compared to all the other values, can that be mode? No, it cannot be the case. Just because it occurred just one time more than the other mode, does it represent? No. Generally this will happen in a scenario. Some examples is you buy t-shirts size, which is the shirt that generally gets more purchased? Is the 40, 42 or XL, small, medium? Which size is more purchased? You can calculate mode in those scenarios. Generally you'll get a trend. But when you take a quantitative data and find the mode, unless it is really representative enough to calculate the mode format, mode may not be the right approach. Having said that, mean, median, mode are used in different scenarios sparingly and as the situation demands. So you need to have a sense of what is your data all about, how do I interpret my data, and which metric is the right metric for me to do calculate in this scenario. Now jumping into dispersion. What is dispersion all about? So you have data at your disposal. The data is not the same value all across. If 100 records are there, 100 records will not have the same value. Each record has its own value. So the data is definitely bound to be spread across a range of values. So how do I calculate the distribution of data around that central tendency? That variation in data is called as dispersion primarily. And we measure the dispersion of the data through different metrics. The very basic metric is range. The range is calculated as a difference between maximum value and minimum value. Like you have seen the challenges with mean, median, mode, the measures of dispersion also have their own challenges. You take range, you know the distribution of the data. What is the smallest value, highest value? I know what is the distribution. Fine. Mean, median are the maximum and minimum value are outliers, and all other values are somewhere lying in the center. Is the dispersion that I'm calculating is a true representative of the data? No. So basically range fails there. Are you getting the concept of range, advantage and disadvantages? So then they went ahead with another metric which we are not covering here called as a mean deviation. But mean deviation also has its own challenges. So then they went ahead and calculated standard deviation. So standard deviation is a more robust and dependable metric in a data set. But standard deviation is also impacted by the outliers to an extent. That's why IQR has come into picture. So while standard deviation is based on mean, IQR is based on median. So that's the connection. So now we touch upon IQR. And there's a standard deviation also that we come into, but we'll first connect with IQR. So somebody has asked about IQR. So now you know the concept of median, right? What median value is. You arrange your data in a certain order, and then we will take the positional average. If it is in even numbers, you take the central, odd numbers, you take the central value. If it is even numbers, you take the middle two values and calculate the average of those two values to come up with median. But IQR, you divide your data into quartiles. Quartile is 1/4, the starting position, first 1/4, second 1/4, which is half, third 1/4, and the fourth part. You divide your data into these 4 categories, and you will see how much data is falling in each of these quarters. First quarter are called quartile, first quartile, second quartile, third quartile, and fourth quartile. Given that you are arranging your data in an order, the number of points in each of these data, each of these quartiles, supposed to be equal. But in real scenario, that may not be the case. If there is a higher concentration happening in your one quartile compared to the other quartile, then there is an element of skewness that creeps into the data essentially. So you calculate these quartiles, and then you calculate the difference between third quartile and first quartile, gives you the IQR. So IQR is basically the range of the data in your data set where majority of the data points, when I say majority of the data points, at least how many points?
50%, right?
50% of your data lies. Because predominantly have 50% of your data lying in that zone, it is a fair representation of your data distribution. That's why IQR is generally a accepted concept while you are calculating the data distributions and measures of central tendency. Does that explain the concept of IQR? The formulas and all, yes, I think it is covered in the course, how does that is done in the IQR, but that's the basic concept of IQR.
What's
What is
positive or negative?
all right? So what is deviation? Let's take the term deviation. Is IQR clear, right?
Yeah.
Okay. So what is standard deviation? To know that, first we need to understand what is deviation. Your deviation is nothing but amount of a difference. But difference from what?
From mean.
Difference with what?
From mean. Each observation, how it is, how much is the difference between observation to the mean? Yes.
Exactly. You have 10 data points in your data set. How each of these data points is deviating from the mean of this data set. You calculate that variation. Sometimes the variation could be positive, sometimes the variation could be negative. So what we try to do is, because the negative differences, positive differences from the mean, if we add up all of those things, what do we get?
We'll get zero almost. And if
you'll get zero. Obviously have to get zero. Then you are not accomplishing anything, you get a zero there. So that's why what we do is you square each of those differences and add all of them. So that is what is happening here. See, mu is your mean, xi is your data point. For all the values in the data set, you are calculating the difference and squaring them. What does the squaring do? The negative sign goes away. Now all becomes positive values. Once you add up all those positive values that are coming in, and then find the square root of that particular value. You divide it by n essentially. So you get the mean deviation that has happened, because this is a deviation, right? You are calculating deviation for n data points and divide it by n, then you calculate the average deviation that is happened. But what is the value that you are getting in when you did this? It is in squared value. It is not the main plain difference. You squared it. To get to the original value, you apply a square root here. Yes, inner root means square, you get that. So that's what the standard deviation calculation works essentially. So you calculate the deviation from mean for each of the values, square it, divide it by the number of values, and find a square root of it, you will get to standard deviation. What is the square of standard deviation? Variance. It's called variance. It is an information point again. Now, coefficient of variation. So standard deviation is calculated at an absolute level, actual number level, the deviation. Coefficient of variation is calculated in terms of percentages. So if S is your standard deviation divided by the average, that ratio is called as coefficient of variation. In which scenarios you use? There is an example that has been explained in the class or in the video. For coefficient of variation. If somebody makes 50 units of sales in a given year and another person makes 75 units of sales in another year, but the person who is making 50 units of sales has a standard deviation of 5, the one who is making sales of 75 has a standard deviation of a 25. Who is more reliable for me? If I have to make projections for next year as to how many sales I can do, who is more reliable for me?
The one with the less, 5.
Yes, but just based on that I cannot get. So to get into that percentage I can rely on, I calculate the coefficient of variation. So I divide the standard deviation by the average, I get a percentage of that particular one. That's what the coefficient of variation is being used for. Then the empirical rule. Now the most important tenet of any data distribution, your data is expected to be in a normal distribution. That is what is called as a bell-shaped. We'll cover bell-shaped normal distribution in the next class when we touch probability, but your data is in the symmetric form, which is a proper bell curve. Then the data is supposed to be a normal distribution, which means in a normal distribution, the average or the central tendency of that distribution lies exactly in the center. If it is not, if the average moves to either this side or this side, then we call it as a skewed distribution. Right? In a skewed distribution, you cannot get mean, median, mode as the same. If your distribution is symmetric, which is the bell shape, your mean, median, mode will exactly become the similar, almost the same values. Then the distribution is generally mean. And if it is normal and bell shaped, if it is bell shaped, the research says 68% of the data falls in the 1 standard deviation distance from the mean. That's the empirical rule essentially. And as I said, there are some distributions which are not bell shaped. You get a different type of a distribution. Then you use this formula of 1 minus 1 by k square into 100% to figure out how many deviations away from the central value are the data distributions lying around. So let's say if you have 100 points in your data set in this particular one, and within 1 standard deviation distance, I have to find out it should be 1 minus 1 by k square. K is equal to 1. 1 standard deviation means 1 minus 1 by 1, which is 0 into 100%. So all values lie in that range. If I had to find 2 standard deviations, essentially here as it says, k is equal to 2, this is 1 minus 1 by 4, which is 3 by 4 into 100%. 75% of the values lies within that particular standard deviation range. That's the Chebyshev rules is primarily used in the place of where the distribution is not skewed. The 5-point summary we touched upon. Box plot we touched upon, how it looks, why the variations occurs. This is the skew I called. So in a normal distribution or a bell-shaped distribution, your mean is at the center and the deviations are there. And let's say you have 1 quarter, first quarter and third quarter like this. And if you do a left skewed, the distribution is more like this. Left skewed means what? Majority of the data is sitting here. Only very few data points which are primarily outliers are lying on the left side of the thing. That's why it's called left skewed. When you draw a box plot for this particular one, the median is more towards the right because that's where the data concentration is there. But there is a more, these are called whiskers. These lines are called whiskers for the box plot. You see a longer whisker on the left side. If it is a right skewed on the other hand, you see a longer whisker on the right hand side. If it is a symmetric distribution, you see equal length of whiskers on both sides, and also within the box, the median lies exactly at the center. For the left skewed, it lies towards right, and for the right skewed, it stays towards the left. It's primarily the line in the box represents where the data is more concentrated around. This is basically the summary of what we all talked about. Quantile plot is again a different way of representing the same things. I'm not getting into it because in a realistic scenario, we don't use quantile plot so much. It's primarily box plot, histogram, and scatter plot that you eventually use on the things. So this is quantile plot. You'll get this information. The video, it is Abhinandan has explained it well. So you can just look. It's about distributing all the data points across from 0 to 100%. How the distribution at 0%, 1%, how the data is getting distributed for a given value that you see for the quantile plot. Scatter plot we already discussed, touched upon the things. Data visualization we touched upon. Correlation. Now correlation is the next important point. So we talked about correlation as a linear relationship between two variables. I think we saw that chart and the maps and how correlation looks. So if the variables are linearly related, which means those two are moving in some relation with each other. If one variable is moving, the other variable is also bound to move. The question is, if one variable is moving upwards, is the other variable moving in the same direction or in the opposite direction? and by what extent. That defines the correlation value. If two variables move exactly the same way, in the same amount of variation is happening, but in the opposite direction. Let's say if x and y two variables, x is going up by 2 points and y is going down by 2 points. X is increasing by 100 points, Y is decreasing by 100 points. They're in the opposite direction essentially. Then this is what you see. They're very much connected, very much correlated, but they are negatively correlated. That's why you see a -1. This is a 45-degree angle that you see for the line. And this is a perfect linear correlation in the opposite direction. And as the data start, there is no ideal scenario like this. Then you see different types of data behaving like this. So a data more and more coming closer. You have seen in the scatter, the pair plot earlier, how the graphs look like. So we were looking at a graph like this essentially, somewhere like this, where you have 0.6 and 0.9 and data distributions. This is a positive correlation. So you see how the graph, so as the graph plotting getting more and more closer to zero primarily, this is becoming no correlation at all. At this point, I cannot find out any correlation between the data. And as I go further on the other direction and the data starts forming like this, I get a positive correlation. So when we are positively fully correlated, perfectly correlated, I get a value of 1. So that's why the value ranges between -1 and +1 for correlation. This is a visual representation of the things. Now let's look at I don't think I have the formula here, but in the video there is a formula that is explained. There are two variables for which the mean difference is calculated from the standard deviation and mean differences are calculated, and it is divided by the standard deviations for respective distributions. Because the differences as you calculate from the mean, if one value is increasing, other value is decreasing primarily, it creates a negative correlation. That's why the formula is calculated in such a way to get these directions. Fair point. Just I request each of you to go back and look at video, the formula that is out there. That section explained by Abhinandan about the formula. If you have doubts about the formula and how that formula reflects this visual correlation, I can take 10 minutes next week essentially to explain this particular thing. And this is summary, basically all the things that we covered in this session. So let's quickly jump onto the case study. Okay. So this is fairly simple case study. There is nothing complex in this case study. So this is about a telecom company who has a lot of customers. The data set is around 3,300 odd customers. So they have the information related to each of the customers as to how many minutes they talk in the daytime, in the evening time, and in the night time, and what are the number of calls. So in this scenario, I think the assumption is that the number of, for us, every minute is equal to one call kind of a thing. But here the minutes and calls could be different. That's why they're capturing differently. How many minutes they are talking, how many calls they are making, and what are the charges for day, night, and evening calls. They calculate charges and international charges, whether they have a voicemail plan, which state they are in the area, then what is their phone number, what is their area code, whether they have an international plan activated or not, how many customer service calls they are making. This is all the data about the customers. Then what we are trying to find, whether the customer is churning, which means they are going away. So they are putting 0 as churner, 1 as non-churner. Is this symmetry data or asymmetry data? Symmetrical. So what are we trying to find here? Understanding the factors for a churn in a telecom company. And I want to know which customer is likely to churn. Normally, the assumption is majority of the customers are with me. If majority customers are churning, I will not run my business only. Normally in a normal scenario, I'll put 0 as non-churners and 1 as churners because 1 would be less. It's easy to identify, but they labeled it the other way, which is a asymmetrical. But that doesn't make a difference for your analysis purpose primarily. Good. So now jumping into the actual data. So again, Matplotlib, we imported pandas and NumPy and Seaborn libraries as usual, the standard ones. Then you read the churn data file from your data set into this particular one. Then you look at how your data is looking like. So your state, account length is, sorry, how long the account has been active. Basically the number of, I'm assuming this should be the months. Let's take this as months. For simplicity's sake, it is not provided there. So how many months it has been active, which area this number belongs to or this customer belongs to, what is the phone number, they have international plans or this thing. So all the data that we touched upon, this is there. So you see churn as false, 2 variables essentially. That is what we want to find out. So the same data set can be used for doing a basic statistics analysis. Same data set you can do for coming up with a machine learning algorithm for prediction. So it's a classification problem. You can use for that purpose also. Okay, now coming to just, I want to find out histogram of the time spent on day calls. How many people are spending time on day calls and what is the distribution? So basically I'm creating a hist chart. PLT basically invokes a matplotlib by default. PLT.hist is like calling a matplotlib function hist, and you're asking total day minutes, and you are clearly saying 10 bins. If you don't specify bins 10, it by default takes as many bins it feels by a formula that is there at the back end. But if you specify 10 bins to be created, it creates 10 bins exactly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it creates the 10 bins essentially and distributes the data across these values. So, and you are plotting on the label x-axis, you are just putting a label of total day minutes, y-axis you are putting total number of customers on this particular one, because this is just a frequency count of the customers by the total day minutes column. You see that what is this distribution looking like? It's a bell curve, not a bell curve.
The bell curve.
Bell curve.
It's not 100% bell curve essentially, because you see there is a more dominance on this side compared to this side, right? There is a higher domination on this side, more this thing. If it is a proper bell curve, this and this would have been exactly the same level. This and this would have been the same level, but it is close to a bell curve that you can come up with. In a real time, this is as close as to a bell curve that you can get with the real time data. Right? So that's the first inference we are getting in. So there is another thing in the Seaborn last time we have seen, which is called dist plot. If you create that with this particular one, you can see a line also. You can use that as an exercise for you. Use the dist plot in Seaborn to create a graph for the histogram for this one. You will get a histogram plus the trend line of that particular one, so you can see how the line is actually looking. So now how do we categorize the churner and non-churner? By the time spent on the day calls. So it's the same histogram, you are breaking it by churn. So you're creating a separate histogram for people who have not churned versus people who have churned. You see the distribution, majority of the people are lying in this bin. Anyone who is talking roughly between 100 minutes and 250 minutes, somewhere around this region, number of time, there's the amount of minutes they're spending in the day, essentially they are unlikely to be churned. But if you look at the total day minutes for those people who have actually churned, you can see that it is flatter distribution that is out there, and it is all across. Only you see a little spike in the center. Otherwise, it is more like a flat spread across all minutes. That's the first inference. So if I want to find out how many people are actually using voicemail plan, it's basic value counts. Somebody called it out. I think Prasad, you said value counts. Now you use the value counts function to get how many yeses and how many no's. How many people have opted for the voicemail plan. Here 922 people opted. Then you use a count plot, which is similar to the value counts essentially. But the interesting piece is you get it graphically and also by a particular variable that you want. Here I want to break the people who have used a voicemail plan and break it by the churn. It's like a crosstab you are doing and putting it visually. So number of people who have actually a voicemail plan, and among them, how many people have churned and how many people have not churned. Same here for the people who said no. Then this is about creating a box plot. We have seen a huge box plot earlier with 10 different years across 12 years. Here we are creating people who have an international plan, activated for international plan. So we have an international plan, yes, international plan, no. And break it by area code. So here are the area codes: 420, 440, 460, 480. There are only 3 areas, I suppose, if I remember correctly. Yeah, see, 408, 415, and 510. Only 3 areas are there split across, but this is the scale it is providing. But the distribution is like this. The majority of the people who have an international plan are across all area codes. There is no distinction. People who don't have are only primarily in this area.
Yes, John.
Okay. So now the same here. We in this one we created a visual crosstab. This is about creating a visual crosstab. That's where count plot and a hue can provide you. This is about actually creating a crosstab. I want to create a crosstab between area code and voicemail plan between two variables. So I simply call PD is the pandas.crosstab, PD.crosstab, and give the two variables you want. It will give you a crosstab. It's the number of people who have a voicemail plan by each of the areas. You get those numbers. You can interpret that data. Then how to pivot information using Python for categorical values. So there is a pivot table function essentially you call. When you do pivot, you are not looking at just by one value. You created multiple layers. So here we are trying to do it by area code as well as voicemail plan. For each of the areas, I want to know people who have a voicemail plan, who don't have a voicemail plan. So yes and no, that's what we'll figure out. So international plan they have. So yes, no, yes, no, you will figure out. And they're also adding one more mention here. So which are all the columns you are looking at? International plan. These are the columns for each of the things that you are looking at for the whole data set. For every column in the data set by area code 408, you are looking at people having voicemail plan. So these are the people who don't have a voicemail plan. These are the people who have a voicemail plan. You're getting it? So this column, this represents international plan, yes or no. This voicemail plan, if they don't have, it is written as no. If they have, it is written as yes. So it tells how many people have that value here. I have a voicemail plan. And for that particular set of people, how are each of these variables coming out to be the distribution? It's basically creating a pivot table, the simple Excel pivot table that you create. You can create it using this particular one. Instead of giving the whole CH, if I can give one variable, it is easier for us to understand. You simply use account length in place of this particular one and use that variable, you can get it. So let's say, for example, CH of churn. Sorry, I haven't actually run the code. If I run it, it will throw an error. But that's what you can do. You simply give a churn here and run this code. You'll get it only for the churn variable to see how it is coming.
Ram, why the AGG function there is length actually? Is it?
Yeah, it's the length. Aggregation function, what are you trying to see? It's the length. You can do length, you can do sum.
It's a count in this case, right?
It's a count in this case, essentially, yes. The length of that. Thanks for pointing it out. All right. Now calculate the total international minutes for all the combinations above. So again, as I said, actually it is done here. So you take one single variable here like total international minutes, and I am doing an index of area code as well as voicemail plan, the voicemail area code and voicemail plan, and I am making the total international minutes for each of the categories. How many are happening? If they have an international plan, no. If they have international plan, you will get values for only those who have a plan. If they don't have a plan, you don't get values for that. So this is a pivot table for that particular one. Then how do we understand the correlation between variables across different columns? Pair plot CH. So you remember the pair plot we did earlier in the honey production case study? We took only the numerical values and did that particular one. But here we have not excluded the other variables that are there. See what is it causing. If you use a variable which is not numerical in nature, which is a categorical variable, the data distribution will comes like this. There are only two values. It is giving you two columns and one column at the end. It's totally three columns. This should be the area code if I remember correctly. See, it's an area code. It is an area code, which is a categorical variable. So it's giving only three values. So it is distribute all values in that particular thing only. There's not much insight you can gain out of it. This can be primarily used to break this particular thing by these categories than including that itself for a map in particular thing. Is that clear? So what you can do essentially is for the same thing, use it variable and say hue is equal to area code. Then you see the same pair plot here that is out there here with three different colors. If there are three areas, it gives you three different colors. You can see the distribution between those things. You can see very different distributions or distributions laying overlap. If I can run this data and let me see if I can quickly do this piece, run it, and then read the data. Why is it throwing an error? Oh, D. Sorry, I need to see where the file is. basically may not be D. Yeah, it did. Good. So let me go here. So you see this chart. Now if I run this, sorry guys, I'll come back with this one. I'll just hold on. But it should ideally give you as to through that one, it shows different levels of that particular one. I'll come. Actually, it is throwing. It is a type error. It should throw like this. For each of these things, you will get it. But
Is it the square brackets now? If you remove square brackets.
1 second. Let's figure that out. Hue order. It's not a hue. Hue is there.
You should put them in the double quotes.
No, it doesn't. It doesn't make a difference. Double quote, single quote.
Is it? Okay.
Hue equal to species. You just put the variable there. I'm just wondering why it is not taking that.
The square brackets was the problem now, because if you see the example, there is no square bracket.
Yeah. You need to use a square bracket.
Possibly. Good. Because I used with CH square brackets, I forgot to remove them. Let's see that. Because there are so many variables and it tries to create.
Yeah.
And so you when you are creating particularly pair plot, you need to figure out what variables actually make sense for you to create it, or create two separate charts looking at the things. See, as I said, it has two different colors, different hues you will get. So here it can be, one can be 0 and 1. I don't know which color. There will be a labeling also. So one is taken as 0 and the other one is 1. Based on that, it gives that thing somewhere at the bottom. Yeah, see, blue is false and red is true. So that's how. So if you look from this lens, you don't, sometimes you feel that one data is overlapping on the other one. You might not see the exact deviations. In some cases, you can see a clear clusters forming. People, if there is the impact of a particular variable, you can see some people who are churning actually on this range versus on the other range. Is there any such pattern that we can identify anywhere? No, there is no such pattern emerging essentially. But if you look at this one, at least I can say that people who are churning are essentially in this zone primarily, except for this bottom, this thing. Just as an example. But this is how you interpret and apply your data for this particular one. Is this idea clear? How I can use hue for getting different things?
Yeah.
Right. So then standard deviation. Simply you call std function, it calculates the standard deviation of that particular function. So the dist plot I talked about earlier. So you use the dist plot from Seaborn along with the histogram, you get the line also of the bell curve, how this looks like. So this data is more or less very much bell curved, bell shaped. The distribution is happening normally. But the challenge with this particular one is, if you forget this line for a minute, if you take the mode has to be the highest occurring value in a particular data set.
Yes.
But in this data set, see what is happening. There are 3 modes. This is called as a multimodal data. You cannot find one value as mode. Overall, this is looking like a bell curve. But what this is not addressing you is there are 3 values which are essentially that are coming up as significant as each other. So then you create histogram for a categorical variable. So churn is a categorical variable. You break it by another categorical variable and you create a histogram. You can create that. So false, true. It is creating 2 separate histograms for people who churned versus who did not churn and which area they belong to. So there's not much of a difference you are calculating. Then area wise churner. So you have 3 areas. For each of the areas, you are calculating who are the people who have churned versus who have not churned. If you see which area is representing maximum churn ratio, can you visually tell me with this graph?
Yeah, area code 4 and 5, right?
So how do we calculate it? It's a proportion of the total number of people, this to the total number of people. That's how you would essentially calculate.
510.
Yeah, 510 is the one that is coming out to be
Yeah.
slightly more. The 408, 510 more or less same, but this is slightly lesser people and more or less the same people. So this has a higher churn rate compared to the other one. The way you get to the graph is you create area code is equal to as type. You're converting this type as a category, area code, because it is numerically, it was trying numerical operations. So I'm forcefully converting it into a category using as type function. And once I create this variable as a categorical variable and then do a count plot between these two variables, I get this. So you can use different types of graphs that are there for doing all these analysis.
Yeah.
So you are applying basically all types of charts. Then you can apply statistical methods. You can do correlation also between the variables. Now you have seen in the Honey production file, you have seen how a correlation is getting calculated. You just need to do a .cor function on the things. So you can calculate, is there a correlation between different numerical variables. But just remember one thing, how do you calculate correlation? I think that is explained in the video. Correlation can be done on numerical variables. When you do a correlation for categorical variables, what do you use? You have seen the video on chi-square?
No, Ram. I haven't heard that one in the video. Maybe I missed it.
No way, not seen.
Not seen it? Okay. I thought chi-square is explained before correlation. Okay, so maybe you can go back and check. I'll also confirm that I have seen chi-square, but
Okay.
correlation is of three types. Essentially, let me put it this way. One, you can do a correlation for categorical variables. One, you can do correlation for ordinal variables and numerical variables. So there is another level called interval. An interval can also be considered as an ordinal in a way. I'll explain the difference between interval and ordinal. So for numerical variables, you essentially use correlation. For categorical variables, essentially you use a chi-square. So in our example that we have seen here, if I have to do a correlation between these two variables, which is an area code and also a churn, both are categorical variables because either yes or no or 1, 2, 3, three different levels essentially. And there is no ordering between these three. It's not like 408 is less than 415 and 415 is less than 510. Just they are three different areas. Say likewise, false and true are also two different categories. If I have to do a correlation between these areas, I essentially go with doing a chi-square example. So I will verify chi-square. If not, we can touch chi-square next week. Then the other example, essentially, the other piece you do is a correlation when the data is numeric in nature. Then you actually get into numerical calculations. But within correlation also, there is a data which is called as a ratio scale. Other one is called as an interval scale. Have you heard of the distinction?
Nope.
Okay.
Maybe they're part of the week 2 course, Ram. Maybe.
I am a little confused. Actually, I thought it is part of week 1. Okay. If I'm missing on the things, maybe we'll touch upon that particular one. Otherwise, maybe next time I'll spend 10 minutes on that particular. It's not a huge concept, but it's something that you need to keep in mind definitely. What kind of a correlation you calculate on what? So this is not explained in the video, by the way, about different types of correlation. They calculate one correlation on numerical data, and he explains chi-square on categorical data.
This brings us to the end of this tutorial on measures of central tendency and deviation. Now, before you guys sign off, I'd like to inform you guys that we have launched a completely free platform called as Great Learning Academy, where you have access to free courses such as AI, cloud, and digital marketing. You can check out the link in the description below. So guys, thank you very much for attending the session and have a great learning ahead.